During the last million years, no less than 1/3 of the Earth's land surface has been affected by glacial ice. In some cases, as here in the English Lake District, its impact is obvious. In other areas, the effects are more subtle. This is the valley of the River Severn at Preston Montfort near Shrewsbury, and it too is a landscape strongly influenced by ice. But the strength of this influence only becomes apparent if a detailed study is made of the deposits into which the river is cutting. These deposits are clearly exposed in a cliff overlooking the river, and it's immediately obvious that they are far from uniform. The surface layers are, of course, soil. Below the soil, for a distance of 1 meter, the deposits are fine, while towards the base of the cliff they change dramatically, becoming coarser and more varied in size. It is the last two deposits which are of particular interest. The fine material is very distinctive, displaying as it does a series of thin layers or laminations. It is, in fact, typical of the sediments laid down in lakes, and in glacial lakes in particular, where deposition is marked by a strong seasonal pattern. During the summer, there is abundant meltwater entering the lake, and this brings with it a large amount of sediment. The coarse material is deposited on the lake bed, forming a distinct layer. During the winter, the lake surface freezes. The supply of meltwater, and with it sediment, ceases, and the remaining material, now much finer, slowly settles out, forming a second layer so thin that the total annual deposition is unlikely to exceed 1 centimeter. If this process continues for a number of years, however, a great thickness of alternating summer and winter deposits will be built up. These are varves, which closely resemble the deposits seen here at Preston Montfort. Could these deposits then have been laid down on the bed of a lake near the margin of an ice mass? And if so, could the material which underlies the lake bed deposits also be associated with a glacial environment? In this case, the evidence is far from obvious, and a detailed analysis of the deposits is necessary if their origin is to be understood. First, we look at individual stones in the exposure. A sample of at least 30 stones is located on a survey grid laid out on the cliff face, the stones being identified by referring to a list of random numbers. Each stone is partially cleared so that its orientation in the deposit can be measured. This is simply the bearing of the long axis from north, a bearing which can be measured using a compass. In this case, it's just under 90 degrees. The dip of each stone is also measured. Once again, it will be represented in degrees, but this time from the horizontal. A clinometer, which is incorporated into this type of compass, is used, and measurement can be carried out without further disturbance to the cliff face. Repeated measurement reveals a strong alignment of the long axes of stones in the cliff face. This suggests that the deposits here could have been laid down in a high-energy environment where sediment movement was rapid and on a large scale. The direction of the alignment suggests that the direction of movement was along the present valley, and that the deposits originated in the Welsh mountains on the horizon. If this is so, can the size and shape of the material in the cliff face reveal more about the nature of its deposition? To examine this, bulk samples must be taken. We use a half-meter quadrat located at random on each of the deposits to be sampled. Random numbers are again used to establish the location of each quadrat. In a coarse deposit such as this, a sample of about 5 kilos is needed. For a fine deposit, such as the lake bed material, the sample can be much smaller. These samples are then taken back to the laboratory. We are going to look at the coarse material. It's first dried for at least 2 hours in an oven, preheated to 55 degrees C. This relatively low temperature reducing the risk of particles disintegrating. It is then weighed prior to sieving, which will isolate material of different sizes. Because the particles vary greatly in size, many sieves are needed and have to be arranged in 2 stacks. The entire sample has been placed in the larger stack and has been vibrated for at least 20 minutes. The stack is then removed so that the sieves can be separated. This is the largest sieve. and the stone from it is obviously rounded, suggesting a fluvial origin. The weight of the contents of each sieve is recorded. The tray under the bottom sieve, in this case containing no less than 3/4 of the sample, is emptied into the stack of finer sieves. Note again the rounded shape of the larger particles. This is sieved for at least 20 minutes, and this isolates the finer fraction of the sample. Each sieve is emptied, taking great care to ensure that all of the finer material is included. The contents are weighed and the results are recorded. These can then be expressed as a histogram. This shows a bimodal distribution. It displays two distinct peaks, one at the coarse end of the scale, representing the stones which were found in the deposit, the other the fine material. It's the coarse material which was most obviously of fluvial origin. Its large size and its moderate degree of sorting suggest that it was laid down, once again, in a high-energy environment, an environment which, given the presence nearby of lakebed deposits, might well have been associated with the streams which discharge from an ice mass. It's generally accepted that the last major ice masses disappeared from this area about 10,000 years ago, but glacial environments can be found in many areas today. This being the case, are similar deposits being laid down in these environments now? The upper part of the Val d'Aran in Switzerland has obviously been recently exposed by retreating ice. Here, for example, is an area of hummocky moraine. And here, even more clearly apparent, is the lateral moraine exposed by a retreating glacier. And this is the glacier in question, the Montmine Glacier, which still occupies the upper part of the valley. A more detailed picture of its retreat can be obtained from a study of the vegetation in the valley. Lichens are among the earliest colonizers of new environments, and here, near the ice front, they're found growing on many rock surfaces. By measuring the diameter of a large number of specimens, always taking care to select the largest isolated specimen of the same species on the rock face, it's possible to establish the shortest length of time during which rock surfaces have been exposed, the lichens being larger on the older surfaces. Near the ice front, only lichens are found. Away from the ice front, the vegetation becomes more varied and flowering plants colonize the spaces between the rocks. Further away still, the first trees appear, and this provides the possibility of more detailed information concerning the rate of ice retreat. For all trees have growth rings, as can be seen from this cross-section, and these can be used to date the tree, 1 year's growth comprising one light band and one dark band. A core can be taken to expose the annual growth and later replaced. The rings can be clearly seen in this core, and the age of the tree can be calculated. In this case, there are 16 annual rings, which means that here, the surface on which the tree is growing must have been exposed for at least 16 years. By examining a large number of trees in this way, an accurate picture of the age of existing vegetation in an area can be obtained. In the upper Val d'Aran, the pattern of vegetation is strongly influenced by the retreat of the glaciers. Initially, the entire upper valley was covered by the ice. As it retreated, the newly exposed land surface was colonized, first by lichens and then by flowering plants and trees. Further retreat led to an extension of the forested area. The time scale of such changes can be determined. In this case, a retreat of almost 2.5 kilometers in little more than 200 years. It's the deposits associated with this retreat which are of particular interest. For here, within a very small area, are found materials laid down not only by the ice itself, but also by proglacial streams flowing from the ice front including streams which enter a small moraine dammed lake. In short, this single valley contains, on a small scale, the main components which may have contributed to the formation of the deposits seen in the river cliff at Preston Montfort. At the edge of the ice, the material deposited is quite distinctive. The overall impression is one of chaos. The entire area is covered, and in places the debris appears to spill over into the ice itself. So much so that it's sometimes difficult to tell where the ice margin is located. This is the terminal moraine of the glacier, a mixture of huge boulders of all shapes and sizes, and of finer gravels. In this respect, it differs greatly from the deposits seen in the river cliff, and a simple test of angularity confirms the difference. For this, we compare rocks with the standard shapes on a widely used shape chart. These rocks are obviously very angular. Those in England were well-rounded, suggesting that running water had been the main agent of deposition, possibly a stream discharging at a high rate from an ice front, like the pro-glacial streams at the snout of the Montminy Glacier. Let's look at the deposits found near these streams. This can be done by taking a random sample of individual stones. To do this, a rectangular grid is laid out on the valley floor. The stone lying directly under each intersection is selected. A minimum of 30 stones should be chosen. Each stone in the sample is then measured. The long, or A axis, the intermediate, or B axis, the short, or C axis. Finally, note is made of the degree of angularity. In this case, the stone is obviously rounded, much more akin to the stones in the deposit at Preston Montfort. Particle size can be determined by calculating the mean of the three axes of each stone, and the sample's size distribution can be plotted, once again as a histogram. There appears to be little resemblance between this histogram and the one for the deposit at Preston Montfort. But the two samples were taken in different ways. The Swiss sample was a surface sample and did not include the fine material. At Preston Montfort, a bulk sample was taken, and fine material was included. Comparison should be made, therefore, only with the coarse fraction of this deposit. Now, the similarities are more obvious. For, although the modal class is larger for the Swiss sample, the degree of sorting, as described by the particle size distribution, is similar. And this, taken in conjunction with the other evidence, suggests that the Preston Montfort material could well be an outwash deposit. If so, are lake bed deposits similar to those seen in the river cliff being laid down in the Val d'Aran today? The streams which flow from the ice front contain a large amount of fine material in suspension. This causes the characteristic milky appearance. Some of these streams are continuously monitored during the summer. Here, an automatic vacuum pump sampler is being used to take samples at hourly intervals. Here is the intake. And here the valves which are open to take the samples. Here's one being taken. And the samples themselves show concentrations of sediment which are as much as 20 times greater than those found, for example, in natural rivers in Britain, even in times of flood. The material is swept downstream towards a small proglacial lake where it's deposited to form a delta. Here, if anywhere, varves will be found, since the discharge into this lake is bound to be highly seasonal. Obviously, it would be difficult to sample the lake bed, but even here on the edge of the delta, the deposits display a clear seasonal pattern. A sample of the deposit is taken, in this case using a box, although other methods are possible. Whichever method is used, however, the sampling must be carried out carefully because the layers must not be disturbed. When the surface is cleared, the layering is more obvious with the different shades reflecting different particle size. Varves are found in the top half of the sample, where the fine material is in fact divided into a number of thin bands. The cross-section can be taken back to the laboratory for further analysis. Samples are taken from each layer, and each sample is dried and ground. It's then weighed. The total weight is recorded. It's then sieved using the finest gauge possible, in this case 0.063 millimeters. The coarse material can then be analyzed using the standard sieving techniques as before. The finer material sample is analyzed in a different way. A small amount of this material is placed in a flask. A wetting agent is applied, which will help disperse the particles when water is added. The flask is then partially filled with distilled water. The mixture is placed in an ultrasonic bath, which agitates the particles. The flask is placed in the particle size analyzer. The liquid, which is constantly agitated, is drawn into the machine through a fine tube, and it's forced through a small aperture across which an electric field has been established. Each particle passing through the electric field produces a pulse, and this can be used to determine both the number of the particles and their size. First, however, the water-sediment mixture must be diluted until the needle on the dial reaches a central position, showing that a suitable concentration has been reached. Then, analysis can begin. The machine has been programmed in this instance to count 100,000 particles, and the results of the count are given as a histogram on the oscilloscope and as a printout. Our aim is to compare this histogram with an analysis of a sample from the Preston-Montfort deposit. The two histograms can be superimposed, and it's obvious that they are strikingly similar. The major difference is in the location of the modal class, the Swiss deposit being larger, but the distribution of the different particle sizes is very similar. Analysis is repeated for a large number of varves in the two deposits, and the evidence that the Preston-Montfort deposit is a series of varves laid down in a lake, and possibly in a pro-glacial lake, is convincing. This being so, what can we say about the deposits which occur in the river cliff at Preston-Montfort? They are undoubtedly characteristic of deposits found near the edge of the ice masses today, and they were probably laid down by streams flowing into a pro-glacial lake, the lower outwash material possibly representing a delta, part of which was later covered by lake deposits or varves. Finally, the presence within half a kilometre of the river of an area of morainic deposits suggests that the lake formed behind the moraine as the ice retreated from this point towards the mountains to the west.